Hi, and welcome to another IBIPSA education webinar. I can see people are still just joining, so we'll get started in just a minute once people have been able to join. So it's great to be back with another BOPTest webinar. Today we're going to be talking to a colleague from UCL, Flavia de Andrade Pereira, and we'll also be talking with Lucas Spex from KU Leuven. This webinar is part of the purpose of the IBIPSA Education Committee. So we exist to identify education and training needs throughout the building performance community. And that includes academia, the private sector, and government as well. And one of the things we do is initiate, develop, and encourage new educational material. We also offer training sessions like this. And a really important part of what we do is to make that open access. So those sessions are available to non-members as well as to members. And we will make the recordings of the sessions available afterwards on our YouTube channel. And I'll tell you more about that at the end of the session. We also exist to promote the development and sharing of best practices in building performance simulation education. And if you've got any thoughts on any of those issues, do please feel free to get in touch. LinkedIn is the best way to join the conversation. So we know that there is a need for novel control strategies and that's growing due to the need to reduce energy costs and carbon emissions and provide flexibility and reliability for the electricity grid. And the BOPTest framework establishes a set of tools and agreed metrics for assessing performance of control strategies. So it's within that context that I'd like to introduce our speakers. So first we're going to have Flavia, who will be discussing her work about enabling portable demand flexibility controls in BOPTest with semantic modelling. After we've heard from Flavia, we'll hear from Lucas Spex, and he's going to introduce YARDS, which stands for Yet Another Residential District Simulator, which is a simulation framework based on DOPTEST. And YARDS provides a test case for developing and comparing the performance of integrated controllers. So it's a really interesting conversation we've got lined up for you. I won't waste any more time, and I'll invite Flavia to share her screen and to get started with the first presentation.
Perfect. Thank you so much for the intro, Palma. I'll start by sharing the screen here. And hopefully you can see presentation mode, right?
Perfect.
Good. Perfect. Thank you.
Thank you.
So I'll jump into it. Hi, everyone. Thank you so much for having me here today in the webinar. I'm very happy to be talking about this work that was a big part of my PhD at UCD, and also a great collaboration with Berkeley Lab, Cardiff, and UCL. I'll be talking basically about how we are looking into how to make this very amazing and novel and much needed demand flexibility controls reusable, portable, applicable in different buildings, and what is the role of semantic model, and how we use BOPTest to test the framework and to prove the effectiveness of what we are proposing. So I'll start with just some context for demand flexibility. As Pamela was mentioning, they are important strategies to mitigate the mismatch between supply and demand. And their importance has been acknowledged quite a lot by different parties. In the EU, they have been set as the center of the EU reform, and they have been estimated that we need some double the flexibility in the next few years. In the global scale, there's also an estimation that we actually need to increase by 10 times the targets that we had in 2020 by 2030. and that we need most of that coming from buildings. So as we see here, there's a lot of potential, there's a lot of need, and where we are at. According to IEA, we are not there yet. Many efforts are still needed to make sure that we can be on track and achieve such an estimation, such target. And there are many different issues, many different barriers. There's a whole value chain when we talk about demand flexibility that needs to be taken into account. But in this research, what I've been looking into is standardization, interoperability, and the lack of having algorithms that can be reused in different buildings. So starting with just an explanation of how I see interoperability and standardization on this context. As you know, buildings are very heterogeneous. So you go to different buildings, they have different data sources, different vendors, different communication protocols, and we ended up having data silos, and to communicate with between each other, those data silos, we have spaghetti arrangements. So which means that for each data to communicate, each silo to communicate with each other, there's many translation between each other, and many ways, all this spaghetti that we have there that makes it very difficult to communicate it and get the data. And even when we get the data, sometimes we don't even understand what the data means. They can be the naming convention that is adopted for identifying those points on those different buildings, they can be very ambiguous, and they can be bespoke and ad hoc. So here is just one example of how in one particular building, they define zone air temperature. And then when we move to different buildings, this name convention can be very different. So when we get data, it's very hard to understand what we are reading from that data. And this is not even only on real buildings. BOPTest was very nice in simulating that real world issue as well. So when we look at BOPTest, and this is just 4 of the buildings that are available so far, and this is also for zone air temperature set points, we can see the different conventions that are used on those different buildings. And the issue with those is that because it's so hard to get the data in different buildings and so hard to understand what the data actually means, when we develop an application, develop particularly a control for a building, it is very customized to that building. And this is another very simple example from BOPTest, where we see that the actual control, the algorithm that is running, it relies on the naming convention that for a particular building BOPTest. And if you wanted to move this algorithm to another building, you have to update this. This is just one example, just simple, but that really happens in different buildings. Many times when we move from one building to the other, you have to redo most of the work. And there is where ontologies, they came into a place. They came as these necessary means for supporting any scalability that and solve those issues with data. So basically, ontologies, they provide this context, they provide this meaning to the data. They allow in a very formal way, they have a logic behind, they have a good standardized vocabulary behind that allows different buildings to be represented in a standardized way. So here is another example. This is a brick model being used to instantiate what different points and equipments and locations of a building, what they actually mean, how they can be related with each other, and then giving some context around the data. The benefit here is that when we instantiated different buildings with the same ontology, then we have semantic models representing those buildings in a very standardized way, in a very consistent way that makes applications being deployed on top of them to be to easily discover the data that we have. So having a conceptual layer that allows us to integrate with the different data in a more standardized, consistent way. And that is the principle of how we defined the framework that I'll be presenting now, and was the topic of this paper here published last year. So basically what we looked into was having a framework that would allow an application to be reused in different buildings. The framework was basically divided into 3 parts for allowing that. The first one, we started by proposing the development. So we wanted to have the semantic models helping. But not only that, we start by looking on what actually makes controls generalizable. What do they need to have? They need to be abstracted to different buildings, to specific buildings. They need to be flexible to different points available on those buildings. They need to be adaptable to different conditions that we find on those different buildings. They need to be modular to allow the reusability of those controls. The other part that we proposed in the framework is more for an automated interaction with the controls, which was basically, so we have controls, we define what the data requirements of those controls are, and we have buildings, and we have semantic models instantiating those buildings. How can we cross-validate these and tell, based on the semantics, which controls are suitable for which buildings? And that was this second phase. And the third phase was the actual deployment. How can we make the controls decoupled from the different buildings, and how they can integrate and instantiated in those different buildings? For this part, we call this a cross-platform deployment that was basically applying interface that would allow to interact with the semantic models and self-configure, instantiate those controls, and then run the controls on those buildings, but also that would allow customization on top. And this part was, I'll be discussing this later on the key insights that we had this here, but it was basically to take into account data and constraints that are not available or not easily represented in the semantic models. To demonstrate this, we tested in BOPTest in a real building, but I wanted to show here just that in BOPTest, we test the controls in 4 different buildings that were very different in terms of having different types of zones, so single zones, multi zones, small commercial, larger commercial, residential, different schedules, different HVAC, and different different baseline applications as well, baseline controls. And we are able to prove it, that a simple rule-based control was just performing shift and chat, was able to run in those different buildings. So you can see the shift and chat for each of those. With very small adjustments, like 2 lines of code had to be changed between one and the other, one building to the other. And it was not even in the control side, it was just on the interface part. And then we also tested in a real building, what the Voltron building. And the difference here was that we added a different interface to interact with Voltron, but the exactly same control was running on that particular building as well. And then we basically conclude that paper saying that, yes, we could prove the portability. But we finish up that paper with also the feeling of, okay, we test portability, it works, but the performance of those controls in those different buildings was quite different. How can we also explore that? And how can we make that a little bit more scalable? Can we have multiple controls? Can we have multiple buildings? Can we not only have controls, but can we have analytics all together on one single instance? And that's when we came up with the library. The DFlex libs is a work in progress still, but I'm going to present some of the ideas and some of the results we have so far. And then for this, the idea was starting, as I mentioned, with having multiple controls being tested in BOPTest and being tested in real buildings, also through Voltron. And then having the semantics framework from the previous paper to allow this connection between the applications, the controls, and the different buildings. And here, adding analytics, so adding sensitivity analysis, adding benchmark, that would allow us to also understanding how well they perform or how different they perform in those different buildings, and if we can manage to take in insights and patterns from that as well. And the final part here was we also proposed a user interface on how we envision this library to be developed and deployed and reused by different users. The test so far has 8 different controls. It was tested in both BOPTest and still ongoing on the real buildings. The controls that we used are from a work from the Berkeley lab. It's also work under review at the moment, where they published different controls strategies for demand flexibility, best practice strategies. And for the KPIs, the analytics part, we are also linking the work with the next 81 Python package on energy flexibility KPIs, which is quite nice as well. And as for demonstration, so we had those 8 controls we tested in different buildings. For the real building here, just one so far that we have the results, and just for one control at the moment. But we can also see that the same strategy, just with the different interface between BOPTest and Voltron, was running in those different buildings. And now we also have the analytics embedded in the library. And a nice part here is that both for running the controls and then for running the analytics, only 2-3 lines of code has to be changed when you selected the building and when you select the control that you want to use, or the building and the analytics you want to use. The building and the control that you wanted to perform the analytics on top of. So it's quite nice, and you're able to manage that. But we're also able to discover some nice insights from all of these. And one was that semantic models was very helpful, but the portability, and mainly when you're talking about controls and we are changing the operation of the buildings, they rely on many other aspects as well that should be taken into consideration when we talk about portability. Number one is the dependence on how we access the data. So how we read and write the data in different buildings, they can be very different. And even when we're talking about APIs, there are different endpoints and different ways of processing the data. So we need a way of decoupling those dependencies and those reliance with the control. And that's how we did it with the interfaces. The other part was mainly here was for the real buildings, that building have specific constraints. And we faced scenarios that the building operator only allow shedding for a fixed period of time. And that was very specific for the building. So that had to be taken into account. Another building had to do stacking on top of the demand flexibility that was being deployed. So also very specific. And for those, we're able to do that by allowing this customization on top of the demand flexibility application, just by having those different functions being added on the interface and then interacting through the interface with the demand flexibility control without having to change the control. Some other things that we also had to take into account was variations in buildings. And here, very common case was the point type. So in some buildings, we have just one set point. In some buildings, we have cooling and heating. In some buildings, we have unoccupied heat, unoccupied cooling, occupied heating, occupied cooling, and so on. So the control, the queries, and everything, they have to take into account that and be flexible to interact with in any option that it comes. Unit of measure, we came across all the different units of measures as well for temperature mostly. Current conditions, demand flexibility works, but it should work in a way that should prevent uncomfortable conditions. And for that, we need to make sure that we understand the different conditions that are in the buildings and qualify those different conditions, qualify those different zones before performing the control. So the control also has to have a set of qualification checks that prevent any unforeseen or any uncomfortable condition. The other part that was quite interesting was the performance variation. So the controls were working as exactly by the logic, but their efficiency could change quite a lot, like from 8 to 16, 20% of savings. And that relied in many different aspects. And then in the paper, we are talking through those different aspects and trying to take out some patterns and sides of how potential strategies work better on potential situations and so on. But we emphasize that when we're talking about portable controls, we also need to talk about performance variations. Some other key insights are also on the semantic side. So semantic models are very helpful, but they do not solve the data mapping challenge in the first place, because we still have to generate the model, the first semantic model. And for that, we still have to understand buildings. And for BOPTest, we generate that manually at the moment, but there is a task right now that is working on automating that process and having a way of generating semantic models based on well-established ontologies. The other part is that current ontologies, they do not cover all the data that were actually needed. So we do support the extension of existing ontologies to also account for those different data needs that are required in this type of applications. And as concluding remarks, what to do with all of this? Some benefits that we believe we have is that researchers can test the portability, test the performance variation of their controls through BOPTest using this idea of the framework. Developers, they can also test their controls, the portability and variation of their performance, but they can also reuse the controls that are available and perhaps create some new products and markets. And in terms of follow-up and related works that we have at the moment, at UCL, we are working on a new project called Build On that use controls and use semantics for enabling portability of controls. At the Berkeley Lab, there's a new project coming up that is on using demand flexibility in different building based on ontologies as well, and 223 and 231 assuring new standards. And the new one X coming up that will have a subtask on semantic modeling for demand flexibility. This is the library. Maybe in the questions I can walk you through. And thank you so much for having me. And big shout out to the team that I work with throughout this.
Thank you very much, Flavia. That was fascinating. I wonder if I could ask you if you could perhaps pop the any of those links into the chat, and then our audience can access them directly. I'm sure lots of people will be interested. We're going to move straight on to the next presentation now. So I'm going to ask Lucas to share his screen. If you've got questions for Flavia, we'll take them at the end. So please, if you could just type those into the Q&A box that should be at the bottom of your screen, and I'll put those to Flavia at the end of the presentations. But for now, Lucas, I'll hand over to you and ask you to start your presentation, please.
All right. Thank you all for being here. I'm very excited to present the work that Hafiz, Lucas, and I have been doing under the supervision of Professor Helsen and Professor de Koning on yet another residential district simulator, YARDS for short. So in this presentation, I will be talking, at least if the slides will continue. I'll start with introducing the topic, why did we make yet another residential district simulator? The middle part will be about how it works, how you can use it yourself, and then we'll end up with a conclusion. So I don't think I need to tell you that the residential built environment is becoming increasingly complex from an energy perspective. To reach our climate goals, we are electrifying a whole bunch of residential services, such as transport and heating, which are now done through electric vehicles and heat pumps, and not through natural gas or fossil fuels anymore. And on the other hand, we're also installing PV panels and local generation in our residential low voltage grids. So what used to be an inflexible, relatively small load is now becoming a much larger, flexible load, but also generation. And due to this increase in electric energy consumption, we get the risk of getting congestion in our low voltage grids, which were never really designed to host so many electric vehicles and heat pumps. Fortunately, this flexibility allows to mitigate congestion, and to use this flexibility, we need some digital twins of our residential districts to do monitoring and control, or a model if you want. Now, when I say monitoring and control, I really mean these two things as separate things. I think a standpoint that I'm willing to take today is that modeling and control are very different tasks. When you're modeling your district, you care about the physical phenomena which govern your district. This is the heat flow in the district, the temperature inside the buildings. Are people still comfortable? What is the energy usage? And you want this to be correct, and you don't necessarily care how this is solved. This doesn't need to be efficient. When you are a researcher modeling a district, you want it to be correct. When we then look at a control perspective, this is much more practical. We get some measurements as inputs, and we want to know which control action to take. So we need some algorithm to get from input to output. And this is a very imperative paradigm where you really have a series of instructions to follow. And if you have a bug in your controller, you don't really care as long as you have good tracking of your reference and people are comfortable inside their home and the heating is cheap. Then it doesn't really matter that there's maybe some bug somewhere in your software or there's something going a little bit wrong. So I would argue that the modeling and the control part, they're very different. And that means that you would also need different tools to do both. So let me illustrate this with some examples. So let's try to model a thermal system in a general purpose programming language. In this case, Python. You can see the function here of the thermal system defining the equations, and everything else is just boilerplate, which you need to solve it and which you don't really care about. Now, there's some problems with this one. If you have a bunch of parameters, then it becomes very verbose to specify. If you switch up the order of the parameters, then you might not realize it, but you may be actually simulating something entirely different. There's no safety checks, no unit checking in here. So this is all, you really need to be knowing what you're doing, and it's not so easy to do or easy to read. Compare this to specialized modeling tools like Modelica, where it's very easy to model something. when we look at this, for example, we see the hydronic circuit of a building heating system, where we can very clearly identify the heat pump, some circulation pump, 2 valves, a floor heating system, a domestic hot water tank. And it's also, there's also as integrated unit checking. You can bundle some quantities together through these ports, which are defined here. So this system, which is probably a couple of hundred of equations, is much more easy to read compared to this Python system, which is really only one equation. So I think Modelica obviously has the upper hand here. When we go to control, this is something you really don't want to do in Modelica. You get these monsters which look like this. So this is in a battery controller. This is a little block which receives a power set point and the state of charge of the battery, and then it checks whether this power set point is actually legal. If the power set point is too low, you can operate in low efficiency regime, so it tries to avoid this, and also make sure that you don't overcharge or undercharge. So you probably didn't get it from the diagram, but when you read the Python implementation of this controller, you can probably see what it's doing. This seems pretty obvious to me. So what I'm really saying here is 2 tasks, 2 tools. And then the problem is, how can we bring these tools together? Because I want to control something, but I also need a model to benchmark my control against. So how am I going to do this? Well, the folks at BOPTest had this really great idea, which I call the simulator as a server paradigm. So what they did is they compiled their model to some binary format, and then they write a whole web server around it, which the controller can communicate with. And this way, any controller written in any programming language can communicate with your simulator, and you can include the benchmarks in the simulator so you can compare the different controllers easily. So it's cross-platform, it's cross-language. I think it's great. It was a great idea, but the main limitation of BOPTest is that BOPTest only supports a very carefully curated set of models that they think are appropriate. And it is actually very hard to do this with your own model. If I want to make a model of a different building or a district or something else, I cannot use their framework because it's really tailored to their models. So that is why we need yet another residential district simulator. We try to open up this BOPTest framework by packaging your models for our simulator, not only ours, not a carefully curated set, but we provide a tool chain which allows you to package arbitrary models. The whole simulator server paradigm is very much the same as BOPTest, and it's then also compatible with BOPTest. So you can use tools like BOPTest Gym together with yards. And we support multiple build tools, namely Daimler and Open Modelica. And we also aim for cross-platform use by using Docker a lot. So this is our main setup. We wanted BOPTest, but we didn't want to use the BOPTest models. And if this is your use case, then stay tuned for the next part, because this is what I'm going to talk about. How does it work and how can you use it? So when we look at this overview, you can see a bunch of components here. Everything that is blue and that has rounded corners is something that needs to be provided by the user. Everything else is provided for you. So what are these things that we need to provide? Obviously, we have the Modelica model of your system that you need to provide manually. We also ask you to provide some metadata about this model that we cannot figure out from our program. This will be compiled to a functional mockup unit, which is a binary program, which will be managed by our simulator server. We ask you to implement a KPI calculator for the server because we don't know what is in your model, so we don't know which KPIs you care about. And you will also need to package this in a Docker image, but this is something that we will show you is not really hard to do. I will be explaining this pipeline throughout our modified tiny cluster example. So this is the model we'll be using throughout the presentation. We have here a small district containing 3 buildings. And these 3 buildings, they are performing ancillary services for the distribution system operator or DSO. Concretely, the DSO provides a maximum electric power consumption profile, and the district as a whole needs to comply with this profile. The degrees of freedom that we have are operating the air-to-water heat pump for space heating and domestic hot water, an air-to-air heat pump for space cooling, and we have some PV panels as well. So this is the model we'll be working with. So let's start by compiling this model to a functional mockup unit, for which we will need the Modelica model and the metadata. So compiling the functional mockup unit you think is very easy. You just press the button in Daimler or in OpenModelica or whatever tool you use, but this is not quite what we're after. If you look at this model here, you can see these little white boxes with the arrows in them. These are what we call read blocks. They indicate that a certain variable is supposed to be readable for the controller. We also have write blocks, which do what you kind of expect them to do. And these read and write blocks, they can be nested arbitrarily deeply in your model. So we need some way to find all of these blocks and expose them at the top level. And then we get this wrapped model where all of the read blocks are exposed and all of the write blocks are exposed as well. So to do this, we have our whole pipeline here. We start from the original model, which you need to provide. And we use OpenModelica to generate the XML description of that model. And then we use a Python script to extract all kinds to find all of these blocks and generate a wrapped Modelica model, which we will then compile to a functional mockup unit. We will also use it to generate some metadata used for the KPIs. And we will also use the original model to generate some forecasts that you can query. So this is all stuff that you do not need to do. You can use Daimler to compile your functional mockup unit if you prefer that, but that requires manual intervention because we cannot package Daimler due to licensing reasons. This seems like a complicated build pipeline, but it's pretty easy to configure. We can provide a small JSON file. And if you look at the slide here, this is 7 lines of JSON, and this is a fully valid file. So it's really not that complex. And yeah, this will give us the functional mockup unit that we need to run the yards framework to run the server. Well, the server, let's talk about that part. This one will deal with the functional mockup unit, so you don't have to, because if you don't know the standard, the FMI, the functional mockup interface, is quite a low-level interface to the model, which is not super practical if you just want to develop your controllers. So this simulator is very similar to BOPTest to the point where we pretty much copy-pasted the code and changed what we wanted to change. The one thing that you need to manage here is the KPIs. And this KPI calculator needs to be implemented in Python. So the yards framework requires you to do this manually. In the case of our small district, it kind of looks like this. So we have 4 mandatory methods. You have the constructor, of course. We have the initialize method, which is called whenever you reinitialize your simulation. So it should clear all progress towards KPIs. And then we have the get core KPIs and the get KPIs absolute function. The core KPIs are basically a summary of all KPIs, and the absolute ones are the extended version. For our use case, we decided to implement the following KPIs, namely being the average coefficient of performance of our heat pumps in individual buildings, the energy cost per building, the emissions, the CO2 emissions of those buildings, thermal discomfort. And of course, on a district level, we want to know what are the violations of our flexibility profile. And then we also implement some helper methods, which are not very relevant here. So this is also something that needs to happen by the modeler. If you don't know Python, that's unfortunate. Now, something to be said about the server is that the server is only really as good as your functional mockup unit. I found in practice that functional mockup units are not always first-rate citizens in all software packages, which means that they do tend to contain bugs and memory leaks, and those bugs and those memory leaks will propagate throughout yards. So if yards is behaving weirdly, that's probably because the functional mockup unit itself is not very good. So this is the one caveat, which I would say. This is something that BOPTest avoids by very carefully curating which models they use and how they use their, and which software tools they use to compile it. In Yards, yeah, we do not have that luxury of carefully checking every model because we are more open. But that said, you probably want to start simulating now. So there's one thing to do, that is to implement the Docker container. This is something that maybe you don't know how to do, but it's actually pretty simple. This is the Docker file for an example here. We basically do this in 2 stages, and every stage starts with the from keyword. You copy over all of the files to the build stage, and then we run make target, which builds our functional mockup unit. So really nothing too crazy. Copy files, make target. You don't need to do anything crazy to do this. And then once we have our functional mockup unit, we can copy it to our simulator and copy over our KPI calculator and some extra metadata. So if you use the base images that we provide, this is actually pretty simple to do. And of course, if you need extra Modelica dependencies, you can install them in any of those stages. So while this may look a little bit intimidating the first time that you do it, it's really not that bad. And then when we have our model, we can try to see what our controls are doing. So this may seem familiar to most of you, I would hope, if you're familiar with BOPTest, because what you're really just doing is making HTTP calls with the API. So we initialize our simulation, set the scenario, set the simulation step, and then we advance it. So to test, for example, our default controller, we would set our simulation step to the entire simulation duration and advance the whole simulation in one go. And then we can query our KPIs. And we get a nice JSON formatted KPI file here. So for every house, we can see what is their discomfort, what is their revenue. But we can also do this for any controller that we want to implement. So same procedure, we initialize the scenario, we initialize the simulation, set the scenario, and then we set the step size. We initialize our controller, and then basically it's a for loop with querying measurements, querying forecasts, computing your control signals that you want to apply, and then advancing the simulation with those control signals. And at the end, you can get your KPIs, and you will get something which has the same format as our original default controller. And the real nice thing about this is that you can really use any programming language of choice. I used Python because it's a very readable language here, but I personally program in Julia, and I can perfectly use the same model that my colleagues who are using Python can use. So you only need HTTP to do this. You can develop your controller whatever language you want. I think this is great. You can also compare the KPIs between controllers because you have the same KPI calculator, but these are all features that you know and love because you use BOPTest. And that brings me to the conclusion of my talk. So the take-home messages, I think, are that modeling and control are different tasks requiring different tools. And one of the best ways to actually separate them, but also bring them together, is the simulator as a server paradigm. And I think with Yards, we have really opened up this tool chain so that you can use this paradigm easily to package your Modelica models to develop your controllers. Yards is currently not available. It's not open source. We are now currently working with it to publish a paper. But once that paper is under review or has been accepted, it remains to be seen. We will make it available open source. So yeah, that was my presentation. I hope you enjoyed it, and I'm looking forward to your questions.
Thank you very much, Lucas. So now we can take questions on both of those presentations. So I think Esther, do you have a question to start us off? And while Esther's speaking, if you could the rest of the audience, if you have any questions, please do pop them into the question and answer box, and we will put them to the panelists.
Yeah, thanks, Pamela. And also thank you, Flavia and Lucas, for your very insightful presentation. It's been super interesting for me, and also for the others, to hear about your research and how BOPTEST can be leveraged for grid integrated building control. One question to get us started, and from BOPTEST, we are always looking for ways to improve BOPTEST and to make it more effective for testing and validating control strategies. And so based on your experience now, working with BOPTEST, what are your key recommendations for the future development of BOPTEST?
That's a very good question. Maybe I can start. One of the things that are very related, and I did mention on the presentation, was the semantic models. So having the BOPTEST test case being delivered and together with semantic models that represent all the data points that are actually available. And this is a work, and I think it's a part of one of the subtask of BOPTest 2, right? That is going on and supported by the Berkeley Lab team. And something else that I don't know how feasible that is, but also having ways that people can create their BOPTest versions of their buildings in a more straightforward way, so they can test their controls in actual buildings that look more what they have in the real scenarios. Because as we saw, in the different buildings, we have different performance variations. And if you go, you can test in many different buildings, but probably when you go to your building, there might be a condition that might lead to a different performance. And as close as you can to test your control in a model that is closely enough related to your building, represent the conditions of your building, would be very helpful. So that could be.
Great, thank you. Lucas, do you also have a few recommendations?
I have actually myself never used BOPTest, if I'm very honest. I also have been interested in district control strategies more than individual buildings. But from my experience with developing yards, a couple of things that I found were that the models themselves use, I think, more outdated versions of Modelica. That I would say that the back end, the models, the compilation pipeline is quite fragile, and that people are a bit afraid to do anything about it. But of course, in practice, you don't notice this as a user. I think one weakness that is also there in BOPTest currently is that it's doesn't allow for uncertainty. For example, when you get forecast, you know that the forecast is completely correct. So I think that would be a very interesting expansion to consider, where you have imperfect forecasts. But yeah, like I said, I have never used it actually.
Thank you, Lucas. Esther, what are the plans for further development in BOPTest? It'd be really great to hear more about that.
Yeah, so there are several areas where we are further developing BOPTest. One is, of course, to have more emulators test cases. Then adding uncertainties, that's also something we're working on. Yeah, different areas really. But because we don't have any, if I see it correctly, any open questions in the Q&A, can I ask another question maybe
Yes,
to our
please
speakers?
do. Yeah.
Lucas, I've read that YARTS is built on DOPTEST, the district optimization testing framework. What is actually the difference between DOPTEST and YARTS? Is there any?
There is a difference, I would say. So we started out by trying to expand DOPTEST, but after some contact with the main developers, it was clear that we had some different goals, where DOPTEST was really aiming more towards the set of curated models and really establishing a benchmark, whereas with YARS, we were really trying to open up the tool chain, which is, I think, a different use case. So we were also asked to change the name to make sure that there is no confusion. Now, the simulator itself is roughly the same. There are some minor changes that I had to make, but it's basically DOPTEST under the hood. But the whole compilation process for the functional mockup unit, that is handmade, that is completely built from scratch. And that is also very different from what DOPTEST is actually doing, where DOPTEST is actually compiling a functional mockup unit of the original model and then using that to generate metadata and get the, but this is not so efficient because you're actually writing the whole functional mockup unit as a binary. You're compiling that takes a lot of time, especially if you use Open Modelica. Where you only really need the XML description of the model to extract the metadata there. So the build pipeline is different. I think that is like the main difference.
Thank you.
Thank you. Flavia, would you like to tell us a little bit more about what you're doing next and how you're extending the work that you've shown here? That'd be really good to hear.
Yes, for sure. So at the moment, as I mentioned, this last paper is still in progress, and we are doing tests in real buildings. We did one last week in one building in California, and we're currently running another, the same control in another building in California as well, both using Voltron as the interface and using mostly of the same interface, but just different agents within Buildon to interact with them, with Voltron to interact with them. And that will lead us to basically finalize this work, this paper in presenting the library and the concepts within the library. And apart from that, as I mentioned in the last slides, there are a couple of follow-up works. So at the Berkeley lab, the same controls that we have in the Flex Libs now, in the library now, they will be developed in CDL, and they will be tested in both BOPTest and real buildings. In California, is a California CSE funded project. So that is one very related work that is going on at the moment. The other that I briefly mentioned as well is this European project that we are involved with through UCL. So we are leading this interoperability work package that is also using semantics to normalize and standardize the data in different pilots. There are 6 different pilots all over Europe. And then we are performing and running controls using the framework and the middleware and all the infrastructure within the project that relies on semantics in those different pilots. And the third one that I mentioned is the DNX 96 that also Esther is heavily involved with, and is on the grid control, grid enable buildings control. Let me check the name. I don't remember the name. Grid integrated controls for buildings. There are different tasks there that are related to developing packages of demand flexibility applications and controls for mostly HVAC systems as well. And one of the tasks that I'll be involved with will be on the semantic side, on basically looking at existing ontologies and checking what it's needed to how they need to be extended to support this kind of applications.
Thank you. You've got a lot on. You will be very busy. We've got another question for you from the audience. Starting by thanking you for a really nice presentation. Do you have any more details about the generic controller that you used? Like, is it MPC? What type is it, and which actuators it controls?
Yeah, so far the logics that we work, they are all rule-based controls. The ones that are available in the repository, they are more like advanced rule-based controls, but because they have very lots of different computation logics inside that do qualification and do the demand flexibility and do ratcheting and do rebound and do everything. But they are still rule-based controls, and the actuation is at the zone level, which was helpful to make the control more applicable to different buildings and different HV systems, as we only need those different buildings to have zone level set points, and that is much easier to find and to define controls that are applicable to those to different type of buildings than coming up with strategies that goes from the plant level and then require buildings to actually have a chiller or something. Although those strategies are also defined in the open specification from the Berkeley lab team. But they are some part of the team from Berkeley lab that is working on making and using MPC and semantics for also controlling HVAC. There is one test going on at the moment in one of the buildings in Berkeley that is running MPC with the support of the 223 Ashray ontology.
Thank you for such a comprehensive answer. I think that's all we've got time for just now. So great question, and thank you for that fantastic conversation. It's been really interesting to learn more about it all. I'm just going to share my screen again and show you where you can find out more. So the recording for this webinar and all the webinars that we do are on our YouTube channel, which is at IBIPSA University. So you can find basically a full education in building performance simulation there. A lot on the basics with series on fundamentals, but then also some much more advanced cutting edge stuff as well, very much like we've been talking about today. So do like and subscribe. The next webinar that we have coming up will be another on learning the fundamentals of building performance simulation, and this one is held in partnership with the AIA. We'll have a presentation from a very esteemed member of IBIPSA and educator in building performance simulation, Ian Boselai-Morrison, and then he will be joined by some panelists who are truly expert both in the simulation tools, like Drew Crawley, who is the originator of Energy Plus, but also in application in the field as well. So do join us for that. There's a QR code there for the registration link, and it will be in your email that you get following this webinar. You can also use the bit.ly link there. And then one last thing from me, as always, is do consider joining IBIPSA as a supporting member. So our supporting members support our work, and in return they receive either a print subscription to the Journal of Building Performance Simulation or an online subscription to that, and you can use the IBIPSA supporting member logo as well. The fees for this remain unchanged, so I've been doing this since 2022, and I've never had to change the details on this slide, so it's still a real bargain, and you can find out more at ibipsa.org/membership. But that's all from me for today, so thank you once again to our panelists, to Flavia and to Lucas, and also to Esther for helping to coordinate and asking some great questions, and we'll see you at the next webinar. Thanks.
Thank you.
Thank you.